All right, hello and welcome back to another episode of This Old Mess. This is a jewel for the Loki staff, and it looks complete, but I was doing something and I decided to try something out a little bit here. Now, it may not look like much right now, but when I flip this switch, it's going to light up and it's going to be amazing, right? No, something's wrong here. Well, I tried this time. Instead of using a white LED, I used a blue LED to give it more of an accentuated blue color when I turned it on. Nice idea, because there's only a layer of blue right here. I wanted to accentuate it a little bit more. This was a completed project, or a project to be completed and a test at the same time. So there is all my complicated circuitry, and I keep changing this one out for a resistor. According to the math the first time, this needed a 100 ohm resistor, and now I'm using no resistor. There are three 3-volt batteries attached to this. That's a total of 9 volts. Well, in all honesty, this should have blown the LEDs. Something's wrong. Today we're going to go over how to determine what resistor you should be using and what exactly I have failed at on this one, because we need to discover what the forward voltage of these LEDs are as well as their resistance. Okay, here is step one. I'm going to use these 9-volt array battery that I have sitting here to connect to one LED, and that will most definitely blow out the LED. So I have the one LED exposed here. The second LED is cut off. This I'm going to install right here where I've been passing along different resistors. So I'm going to trim this. And now I'm going to test its voltage, or its resistance. And across here, this green bar is my my ohms. This is an analog reader, so it's a little bit different than the digital ones. Across here is ohms 0 to 500. So when I select this, I want it times 1 ohm, which is this right here, times 1, times 10, which makes that value 100, times 1000. I think you get the point here. But there's also, if I make contact, this is the audible. Audible is handy just to make certain that you have voltage. That's all it is. So at 1 times, when I put these two together to calibrate it, it should read 0. It's a little off. So I'm going to use this wheel to set it at 0. Cool. Now, test the resistor. Cool. It is, by the way, a 1000 ohm resistance. So 1 times is too low because 1K is way over here. It barely moved the needle. So we got to try it again. All right, there we go. It's above 100. This is a very high resistance. It's more than 1000. Very hard to get a delicate reading on this, but it's just over 1000 ohms. It's a plus or minus 1% value, so that could be anywhere between 1100 and 1000 or 900. So it's marking itself just slightly over 100, which means that this is just over 1000 ohms. So that should be good enough. At this point in time, I really wish I had a digital one, because I can get the very specific measurements so that I can make very accurate mathematical calculations. So this is a huge disadvantage to using an analog version. Forgive my fiddling around on my volt-ohm meter here, but I am examining the variations of voltohms or ohms on all of my resistors here, or a quick sampling of resistors, and then I'm going to get to soldering away so that I can swap out the resistors. I determined that it was at 1.1 thousand ohms, or 1.1K, by going back and forth between the 10 times and the 100 times and seeing where it laid. We'll go over that in more detail. But I'm just going to simply quickly unsolder the old connections and start dismantling everything so that I can get to adding the resistor as it should be. Okay, so there's my 1.1 maybe ohm resistor against one LED, and it should light up. It does, but barely. So I'm going to turn it on. Now I'm going to figure out how many volts it is. Ten value, there's the 10, 50, 250, 1000, 10, 50, 250, that's the 1000. So 10, 50, 250, and I am going to use the 10 to see how many volts it is. So instead of going this way, it's actually going to go this way on the meter. It's already set to 0, so I should see it hit somewhere around here. That's where it's supposed to hit, but I have a feeling it's actually higher. I don't know. We're about to find out. Alright, it is on, but there's barely any light coming out of it. Let's test the voltage. .8 volts. Okay, so here's what we've learned on this. My resistor, which is that omega horseshoe looking thing, equals 1.1K, or 1000. That is the resistor. Usually this is the value that we have to find. So usually we're asking, what is this value? And we want to know what we want to put on there. But in order to get there, we have to know three things. Number one, how much voltage you got here. And that's one thing that we haven't tested on this, is how much voltage. But the LED is number two. The LED has two parts. And is this writing sideways going to be okay for you? First part of the LED is voltage. And then the LED has an amperage requirement, usually listed in milliamps. That is 1/1000th of an amp. And these are the two values that we need to know from the tech sheets of the LEDs. Well, when I got these LEDs, they had no tech sheets on them, none whatsoever. And I have no idea what it is. I assumed that my blue LEDs value were at 3.4 volts. And that is the information I was pulling up online. It is obviously not 3.4 volts. It is 2.8. Huge difference there. Since it is 2.8 volts, something here is a little amiss. So I need to get the specific voltage of my battery. Three-volt button cell batteries with low milliamperes themselves. They don't burn out LEDs very easily. Three volts exactly. volts exactly. 3 volts exactly. So I'm at 9 volts. When you run these together in a series, you just simply add the voltage. Some people would use a 9-volt battery. Some people would use AA batteries. There's all kinds of different batteries you can use, but we've just measured the only value we need on there, the voltage. Each one of those are brand new batteries, so they're 3 volts, fresh batteries. Okay, so these are the 3 elements that we need, but we're missing one, the milliamperes. Now, there's a whole bunch of math that you can use with all of this information to determine this, and that is what I'm going to do now. In fact, I'm not so good at this. I'll tell you a secret. You know, I'm not so good at electrical engineering. I'm a novice cosplayer, cosplay creator enthusiast. So between you and me, my level of experience with this is kind of novice, and I've learned that you don't need a lot of information. So let's just stick with the information that you need and skip all the crap you don't need, which is this. There's my corrected values. Here's the ones I normally use. But look, I have no idea what the milliamps on that are. So, let's duplicate the test. On a little bitty LED like this. What side is positive? What side is the negative? Short end is negative. Long end is positive. You should hopefully not have to determine this in the same way I did it. These values should come with your LEDs. But given that these were the cheapest ones on Amazon, I'm feeling the consequences of such a purchase. So with that said and done, and now that I have these values, and now that this one has turned itself into a nigh useless mess, it is time to actually fix it to the best of my ability and get the proper resistor on there. So how do we do that? First, we choose an LED. I can go with this one, or I can go back to blue. Difference is very minimal between the two. This one is 2.8 versus 2.5. Now, that is the forward voltage that they are pulling. That should be on your technical data sheet, whatever it's called. Something similar to this for all my resistors. Got a little sheet on there with all the pertinent information telling me what's what. And just in case you want to know, that's how I knew it was plus minus 1%. Because on my resistor, which I have just misplaced. Here, I have a whole bunch of them. Because my resistor, yeah, these are a 4 or 5 band resistor, starting with the first one to the last one. Each one of those means something, and it creates a number. Now, if I'm not certain whether I should be reading red or brown first, I've already ascertained that, because each one of these are 200 ohms. Brown one first, that's the number 1, 0, 0, 0, or let's see here, the fourth one almost to the end, is the multiplier, and that one is, oh yeah, this way, 2, 0, 0, 1 times multiplier, plus or minus 1%. If you read it this way, it would be 1, 0, 0, 1 times multiplier, plus or minus 2%. So since I've already measured these and know that they're 200 ohms, I know that's backwards, and I gotta flip it over. So if you ever wanted to see this yourself and you have no idea, look, it's a whole bunch of colors on there, and you have no idea what they mean. What am I going to do? Well, back to this. 1 times ohms, calibrate it. Boop. A little high on there, let's fix that. And on an analog meter like this, there is this silver stripe. That is so that I could orient my eyes directly above that needle by looking at the reflection on that silver stripe. So I know exactly where it's pointing at when I have the reflection line up with it. So when I do this, I look at it through the lens, and I know I'm right at 0. Well, I'm pretty darn close. If this were a digital, that is not necessary. So I'll show that to you real quick. Can you see it? When I move it around, you can see the reflection. Maybe you can, maybe you can't. So what is the resistance? My needle says 200. If you don't know how to solder already, then this is not a video for you. There we go. Here is 2 9-volt batteries running in parallel. I usually run these in sequence, but the difference in sequence and parallel and batteries, that if I only have 1 battery, it'll still work. When I put the second battery in, it'll be at full voltage. Now the dangers of running it with 1 battery, which is why I usually don't have it parallel like this, is because if I have only 1 battery, it causes the battery to drain faster as the LEDs attempt to require more volts out of it. So this is a temporary setup, and it was a test because I was running 3 batteries, and I wanted to run 6 volts and 3 volts and 9 volts to try to figure out what was wrong with these boogers. But we're beyond that now. So this is my test array. And now what I need, actually, is my LED. I still want to use the blue ones. Forgive me for that. I've been eyeballing these. And I'm going to modify this so that they handle them better. Alright, so back on the lesson of soldering. This is called tinning. This is self-fluxing wire, which means it has flux in it. And look at that. Nice and smoky. And I got a nice silver bead on there. That smoking is the flux. And when it stops smoking, that means there's no flux left. What flux does is, since this is metal, it's not a drop of water, but it behaves like one, it lowers the hardness rating. I guess in comparative water, that's the best way to put it. Lowers the hardness rating so that it flows. It's like softener. And chemically, what it does is it removes oxygen from the equation so that they create a bond. Oxygen is a corrosive chemically, and prevents chemical adhesion. This is why in space you get what they refer to, what do they call it? When you're in space and you have two similar materials make physical contact with each other and they instantly weld, just like this. And, hey, focus. And the reason why this is not like this, because it's just a solder. This is the solder making complete contact with the metal without an oxygen layer between it, and that's what the flux does. It gets rid of the oxygen. So now that that is there, it is as good as, well, almost as good as actual metal on metal, as if it was one contiguous piece. Almost as good. Almost. All right, I need this switch. So I used JB Weld on here. I used JB Weld on both sides, and it didn't stick. I had to end up using super glue on both sides, and the super glue stuck better than JB Weld. Cool. All right. So conclusion from that was supposed to be run in serial or series, and they have to be run in parallel. So they're both getting the same voltage from the same source. And now we need to know what resistor we need to put on here. So there is a calculator that you can get on your phone that will deliver the answers for you, and this is the information you need. How many volts this is in total, which we've tested on the voltometer. We know this is exactly 6 volts. The forward voltage of your LEDs, which is what we figured out earlier, and that should be on here, forward voltage, 2.8 volts. And the milliamperes on these, 6 milliamps. So we know that these are 2.8 volts with 6 milliamps on the LED. This is actually pretty low considering their type. Let's switch to the phone app and show you some screenshots about how that works. This is my phone, and it's just a screenshot, so there's no moving pictures here. Oh, well, there's a slideshow here, but there's the little app that I found. It's called LED Resistor Calculator. I like this app because it only focuses on what I need to know. It does have some other tools on there, but I don't care. So let's pop into that real quick. Right now, while we have this open, I've already fiddled around with it to come up with a actual calculation. So let's go over what we see here. In the big green letters at the top, it says 150 ohms. According to the information that I've put in, that is what I need to find. I need to find the equivalent of 150 ohms in some shape, form, or fashion, a combination of resistors or one resistor. It says it suggests 180 ohms, just to be certain that I am not under resisting. But I don't go by the suggestion, I go by what I have. Now, if you're using larger batteries, do stick with what it suggests. Going on, there is the voltage input on here, and that's 6 volts. Then there's the LED voltage, which we spent most of this video trying to figure out, and that is 2.8 volts. Then there's the LED ampere reading, which is 6 milliamps. Now these lower values, the LED voltage and the LED ampere, those are the forward voltage and forward milliamps. And that's important. The last thing that's on here is how many LEDs we have. Now, it sticks with the pertinent information. That is what we found out. I don't have to tell it anything else. I don't have to do any more thinking, which is a fundamentally great thing to have on a single app. So this is why I suggest using this particular phone app. You don't have to use it. You can find another one. But this is something that I want you to be aware of. In order to actually figure out how many ohms we need to resist, there is one value that we must have on here, and that is the difference in how many volts we are over. As such, if we are using a 9-volt battery and we are using 2 LEDs at 3 volts, the over voltage is 3 volts, because 2 LEDs at 3 volts, which is 6 volts, minus the 9 volts is 3 volts. We have to get rid of 3 volts. And that is the most fundamental important thing on here. This already does that subtraction for you. It knows that we have 2.8 volts being consumed from each LED for combined total of 5.6 volts. And it knows that we have a supply voltage of 6 and we need to get rid of 0.4 volts. So it does that calculation for you already. And it also includes the LED amper in there as well as part of the calculation. The calculation is complicated. So just those 4 values, there you go. You're done. Move along. We spoke earlier about single, series, and parallel. Single is 1 LED. Series is the handhold LEDs where you have an LED negative connected to the next LED positive, and then another LED connected to that LED's negative, and so on and so forth. It's a daisy chain of LEDs. Not all LEDs can do this, so be aware that your LEDs may not work in a series. Your LEDs most likely will only work in parallel, default to it. Now we're going to move on to a different one. I went ahead and did the calculations based on what I thought these were initially. So I want you to see this. It now says 75 ohms. Now that's a big, huge difference, but look at the values that we've changed. We went down from, went up from 2.8 to 3 volts, and we have an LED amperes of 20. Now, when we're low values like this, like below 100 ohms, the batteries themselves are actually supplying about 10 to 100 ohms of resistance themselves. 1 ohm is extremely small. 1,000 ohms is still pretty small, but pretty powerful. It can stop low voltage things from doing, anything. Much of anything. So the difference is significant in relative sense. We're still dealing with very tiny values here. So when it says 75 ohms, I usually just completely ignore it, because remember that first rule, my voltage minus the LED's consuming voltage, or the forward voltage, equals how much we have to resist. And 6 volts minus 6 volts is 0 volts. So technically, I would not have to put a resistor on there at all, but it is still a good idea. Moving on to a different example. I know that a lot of us use 9-volt batteries, and this is a great example of the difference between a 9-volt and a 3-volt battery. So here we are with a single 9-volt battery in math only, not a physical one. And we have 1 LED. I notice I changed the number on there. So we have 1 LED with the assumptive forward voltage of 3 volts and LED ampere of 20 milliamps. That's the industry standard for most LEDs. So different values in that have different meanings. The lower the milliamps, the more powerful it is while consuming less electricity, which is good for the batteries. So if you have a 9-volt battery, you have 1 LED, its forward voltage is 3, and you know it has a 20 milliamp rating, then you need 300 ohms on there. Not putting that 300 ohms on there will burn the LED out. Back to our initial calculation. Here is a difference between series and parallels in the ohm rating. notice that it is different, and I'll have to go back and show you the appropriate one because the first image I forgot to hit the calculate button when I changed the values. So we'll see what the actual resistor we need to put on there is in just a second. So here we are. This is the series. This is the daisy chain, the negative terminal on the LED connected to the positive terminal on the next LED. This is a series, one after the other. And if the voltage, if we're using the same LEDs we had, and they do work in a series, which we know they do not, but if they did, we would only need a single 66 ohm resistor on there. Just one. And just as an FYI, it does not matter if the resistor is on the positive or the negative terminal. Electricity flows universally through the entire circuit, so it does not matter where the resistor is as long as there is a resistor. So there's the answer to this formula. It's still below 100, and it's questionable if you actually need it on there if you are using button cell batteries. If you use AA batteries, 9-volt batteries, or whatever, if you use anything larger than a button cell battery, you should never not put a resistor on there. And I want to emphasize that because someone is going to make this mistake. They're going to get a AA battery, and they're like, "Oh, I could test it with this AA battery." It's going to fry your LED. It most likely will. I promise you. Here it is, the LED resistance calculator hitting the calculate button on the forward voltage and the ampere that we spent this entire video trying to figure out with our 2 button cell batteries. We need 266 ohms. And yeah, so notice on there it says suggested 270 ohms. Of course it's rounding up. That's kind of the obvious thing to do. Now what we need to do is quite simply plug in 266 equivalent thereof ohm on there. And I'm gonna do something a little screwy. I'm actually gonna go under because I don't have a 270 ohm. I have 220 or somewhere in there, and 240, and then I have 470. So I don't have anything, and I don't want to daisy chain a bunch of resistors together, which you can do if you put a 100 and then a 50 and then 2 10s resistors, and you daisy chain them all together, and that equals 270 ohms. It doesn't matter that they're daisy chained together. They can run in a series like that and not change the math at all. It's just as long as the total of the resistors equals what you need it to be, you're fine if you use 13 of them or you use 1.
So my phone's running out of batteries, so no more flash. But this is the LED, or the resistor I chose, because the calculator said I should have about 250 ohms resistance. This and these are rated at 220 ohms. They're the same color bandings, I think. No, they come up as the same resistance value on my volt-ohm meter, with one exception. This one is slightly higher at 240 ohms, or this one is just 220. So the 220s I'll just throw over here, and I'm going to use this one. Okay, so here is our completed circuit. 6 volts, 240 ohms, 2 LEDs. Still pretty good. Still a lot of brightness on there. That is a lot of brightness, and I really like that. Now, I could bridge the resistor on there real quick with just simply a piece of scrap metal. Ooh, look at that difference. Now the question is, should I run it with a resistor or without?
The truth of the situation is you should always run with a resistor of some sort. And here is why. The simple truth is these batteries create a spike when you plug it in. All my math. So let's use this space right here. There is going to be the zero current line, and it doesn't matter what the voltage is, but when you have no current and then you hit the switch, your current runs at peak. Whatever your battery is rated at, say if it's a AA battery that runs 1800 milliamps, it goes right to that point. And then it does this. It spikes and then it trails down. The fresher the battery it is, the higher this spike is. When there's some life to it, it does that, does a little bit less, but it still does that spike. And a LED will have an upper and a lower. It's actually not 2.8. Right now we're running at what? 2.8, yeah, it's not 3, it's 2.8. So it'll have an upper and a lower. Say 1.5 volts is the low end, where if your battery gets to be so old, it can no longer maintain 1.5 volts, and it falls in that line, you'll flip the switch, it'll come on for the briefest of seconds, and then nothing. It'll be a dead battery. So if it can't maintain that, it'll drop below. But a fresh battery, if it goes above this line and maintains for so many cycles on the LED's life, it will kill the LED. The LED will burn out and it won't do anything. So when we introduce a resistor onto this, as we have done right here, we change the behavior of this area right here. So it'll still spike, but the resistor eats this difference. So it doesn't matter if it is a small resistor. I've got them down to 0 ohms right here. If you run into 20 ohms or 10 ohms, that was the original recommendation, was 10 ohms on a default on here. So 10 ohms and you would be fine, theoretically. And the resistor turns excess voltage into heat. So this literally generates heat. It generates an extremely small amount of heat because of the type of resistor it is. There's other types of resistors that are very big and they handle high voltage values. Even though they may have 10 ohm resistance, they may be able to produce a resistance to 30 amps. That's a different story. We're not playing with that. We're doing on small 1 amp or 1 milliamp or whatever rating this is. It's the lowest ratings of resistors there is, common for household electronics. So now that we have a 240 ohm resistor in there, what would happen if we changed our mind and said, I want to use 100 ohms? Here's one right here. Ain't this handy? The rule of electricity is it will go through the easiest path. So what does that mean? That means that when I hook this on here, it's going to say, oh, hey, this is the lower value resistor. I'm going to skip that resistor because it's 240 ohms. So this should brighten the LED up. Yep, there it is. Brighten up. Just as we arced it with the piece of metal and had no ohms. That is really bright. Dangerously bright, actually. So, even though this is still running with the recommended ohms, it is running in the value at which I won't burn these out. If it is not bright enough for you, increase the number of LEDs. They're cheap, so it's really easy to do. You might have to change your array, more batteries,
and you'll be just fine. So remember the rule of thumb, what the information that you need, and the calculator should hopefully do the difference for you. If it does not, I should have already told you how to double check that and change that, but we're playing around with things like this, and the last thing you want is to have a completed cosplay piece burn out because you decided to get too frugal or conservative with the resistors.